Let's say we have a problem like this. A first point mass m1 equals 54 kilograms is placed 27 meters from a second point mass m2 equals 6 kilograms. Find where a third mass m3 must be placed so the net gravitational force on m3 is 0. So here's m1, here's m2. They are separated by 27 meters. m3, well, I know m3 cannot be kind of over here closer to m1 because if it were closer to m1 than m2, it would feel a much bigger force by this larger mass. And the force of m2 would be smaller, and the two forces on m3 wouldn't cancel out. So to get the two forces to cancel, I know m3 is going to have to be closer to m2 than it is to m1 because m2 is a smaller mass, so naturally it will produce a smaller force. And the way we increase the force of m2 is by bringing m3 a little closer to m2. Okay, here is how we set up the problem. We know that what we're trying to achieve is that the force of 1 on 3 is equal to the force of 2 on 3, like that. And of course, each of these F's, each force here is a gravitational force. So for each, we can replace that F with Newton's law of gravitation, which says take the constant, big G, which never changes, multiply it by the two masses, and divide by the distance separating those two masses squared. So we can do that on the left, we can do that on the right. This here is m3, so that's a 2 right there. And this is r23 squared, like that. And over here, this is r23. Sorry, 1,3 on the left. Good. You look, you see that the big G's cancel, the m3 cancels, and if we rearrange, then what we get is m1 over, let's see, m1 over m2 equals r13 squared over r23 squared. And I'm just going to call it, I'll continue like this. And this is what we get. Now, what that means is that r1, if we square root both sides, right, square root this side and square root this side, then this squared will go away and this squared will go away, and we'll be left with, on the right side of the equation will look like this. Let's see if I can erase this. The right side will look like this, r13 over r23, because I've taken the square root of the whole right side and those squareds went away. And the left side will be square root of m1 over m2, and that means we have square root of 54 over 6. 54 divided by 6 is 9, as we know. And the square root of 9, right, so under the radical we have 9, this is all 9, and then the square root of 9 is 3. So this ratio equals 3. Okay. Now here's how we can use this ratio to solve the problem, right? We're going to find r1, 3, and we're going to find r2, 3. And we're going to do it without using the quadratic formula. So here's an easier way to solve without the quadratic formula. r13 over r23, that's a ratio, right? So we could write it as 3 over 1. In other words, if we multiply the numerator and denominator by x, where x is just some new number, comparing the numerators of these, of the left and the right, okay, here's the left side, here's the right side. Comparing the numerator of the left and the right gives me r13 equals 3x. And comparing the denominator gives me r23 equals 1x, or just x. So if r13 plus r23 is equal to 27, I can replace r13 here with 3x, and this I can replace with just x, and I get 3x plus x, equals 27, or 4x equals 27. And solving for x, I see that x is 27 over 4, or x is equal to, let's see if I can erase, I know, x is 6.75, oops, x is 6.75, right? So if I look again right here, now that I know x, I can calculate what R13 and R23 are easily. 3 times x is just 3 times this, and that gives me 20.25 meters. And R23 here, this relation says R23 is x, so R23 is 6.75 meters. So let's just quickly review how I got here. Where did what did I start with? What steps did I take? How did I get to this solution? Well, alright, back to there. The first thing that I did is I set the two forces equal, because what we're trying to solve for is the distance at which those forces are equal. So this is our starting criteria. So we write it down. Then I replaced both sides with Newton's law of gravitation. Then with a little bit of algebra, I solved for the ratio R13 over R23, and I got it equal to 3. Using that ratio, I defined a new number x, right, such that R13 was 3x, which I got by comparing the numerator, and R23 was simply x, which I got by comparing the denominator. Right? Then I added up R13 and R23, showing that that was 27 meters. I replaced R13 with 3x, R23 was replaced with x. I solved for x, right? After substituting into this equation, I solved for x. I found x was 6.75. I used that x and I plugged it back in, right, to here and to here, and I solved for R13 and R23. And that, I think, is a simpler solution than using the quadratic equation. And it is kind of elegant in that it uses these ratios, which I like. And let me just, for clarity, write in, remember here, R13 is the distance between M1 and M3, and that is so messy, I'm going to write it again, R13. And this here is the distance between M3 and M2, that's R23. So you may not have been clear on why this was true. Why did the two R's add to 27? Well, if you look at the picture, this is R13, that's R23, and when you add this distance with this, you get the total 27. And you can verify that these distances, if you'd like, you can verify that these two distances are correct by coming back to this equation, I suppose, right? And substituting in for M1, R13, right? Use this value for R13, substitute into M2 using 6, and substitute into R23 using 6.75, and make sure that the left side and the right side are in fact equal. And that is how you solve.